our next presentation is from Robert Lois.
Yes.
From Pittsburgh.
Yep. And
Okay. Oh yeah. And initially we had like agreed on a very cool title of like only abbreviations of CPS and FHE.
Yes.
So it's fully homomorphic encryption for cyber-physical systems, and it's very interesting to see that like actually in the real world being used. I've only seen FHE so far in theory papers.
Yeah,
so
absolutely.
Thank you very much. I'm gonna find your presentation.
Okay. And you're Joel, correct? Or was I
Felix.
Felix? Okay. Yeah, I was emailing Joel. I'm not sure if he was in the room. Hectically last night, sent him like 6 different iterations of my slide deck. So I feel terrible having to give him so many to comb through. Oh, right there, yeah. Great. All right. Hello, everyone. I'm Robert Lois. I'm a graduate fellow at INL in the Department of National Homeland Security. Also a PhD candidate at the University of Pittsburgh, and actually excited to also be defending this summer. Looking forward to that. Very grateful to be here. And to give you guys a brief glimpse into some of my research. This is actually from a paper that we submitted to the American Nuclear Society. It's a best paper finalist, and I'll be presenting that next month in June in the Chicago conference. So the title of that paper was a hardware in loop approach to realize a fully homomorphic encrypted controller for advanced nuclear reactors. So the goal of that research, that paper, was to enhance the security of these advanced nuclear reactors that are semi to fully autonomous and designed with remote operation capabilities. So what advanced reactors are, they come in 2 flavors, small modular reactors or micro reactors. And I'm sure you guys have seen them in the news cycle recently with the generative AI and LLMs and how much we love them and how much energy they're consuming at data centers. And pretty much what they want to do is plop some of these micro reactors right in the parking lot to power those data centers. So they operate at 1 to 200 megawatts electric, as opposed to 1,000 plus megawatts electric for your conventional nuclear reactor that you see with the large cooling towers or the one that Homer Simpson operates. So what we want to enhance the security of are these remote operation capabilities of these remote operations of micro reactors themselves. What they are is we have some operations center that can monitor and control a whole fleet of microreactors that may be distributed geographically. And if we can zoom in on one of these legs, we sort of get this high-level architecture here. And this is where we demonstrate our threat model. So quickly, a remote operations center, we have a remote operator that has some workstation HMI that can monitor and provide commands through some unsecure remote communication network to the microreactor facility. And in the microreactor facility, we have our standard control loops that are has control signals and sensor signals that go and interact with the microreactor. So in this paper, we have this threat model. A passive adversary can intercept and analyze those plaintext communications through this bi-directional communication network. Its capabilities extracting sensitive information about the operational parameters, system dynamics, and control strategies. And our security goals: we want to ensure end-to-end confidentiality, a bidirectional communication. We want to protect the set point commands by the remote operator, any sort of control parameters that may be sensitive to operating the microreactor, sensor measurements, and actuator signals from any adversarial inference. So how can we achieve that security goal? Well, we propose using a fully homomorphic cryptosystem suitable for linear time invariant control systems. What is fully homomorphic encryption, or FHE, for those of you who don't know? We have some message in the clear or in plain text. When we go ahead and encrypt it, we're in the ciphertext space. And unique to the ciphertext space is we can perform mathematical operations on it and get a resulting new ciphertext such that when we decrypt it, its result would be the same as if we performed those same mathematical operations in the clear or in the plain text. So this is the end-to-end confidentiality that FHE provides. And to give you some sort of high-level block diagram of how we want to apply that to our control loop from the microreactor operations center to the microreactor facility itself. We have our physical process, which is our microreactor. At the sensor interface, we're going to encrypt at every time step our sensor measurements. Similarly, for the reactor operator set point, at the set point interface, we're also going to encrypt that input signal. Inside the FHE integrated controller, we're going to perform encrypted digital signal processing to get some encrypted actuator command, which then we will go send to the actuator interface for decryption, and then it'll go on to interact with the physical process. And how did we do that? We did that with a hardware-in-the-loop approach. This is our experimental setup. What it enables us to do is for real-time analysis of our FHE-based control of a small, advanced, modular, high-temperature reactor, or SMARTer. In our lab, we give it the Boston flavor of SMATA. So the SMATA reactor, what the simulation is we have this high-level fidelity Simulink model of the SCADA system and the distributed control system that is being run. And what SMARTer is a conceptual design for a fluoride salt-cooled small modular reactor that was developed by Oak Ridge National Labs. So this is sort of the collaboration effort between us, University of Pittsburgh, and other national labs as well. So yes, the SMARTer Simulink model was developed at the University of Pittsburgh. It is a design by Oak Ridge National Labs. What enables us to have this hardware-in-the-loop approach is this arcade, which was developed by Sandia National Labs. Here's the GitHub here if you guys are interested in using it. It is an advanced reactor cyber analysis and development environment. It's a collection of tools designed to enable researchers like us in this room to perform cybersecurity experiments in this sort of hardware-in-the-loop effort. And also the components that are within Arcade are this data broker and this endpoint. The data broker is what manages the real-time simulation of the SMARTer Simulink model, and the endpoint is what broadcasts the sensor values to a hardware, whatever hardware in the loop there is. It receives updated control signals and any reference set points from some external HMI. For our hardware, we chose a BeagleBone Black. It is, likened to a Raspberry Pi. It is just a microcomputer. And this is our hardware in the loop, which is an encrypted proportional control, which goes on through this crypto system and goes to interact with the SMARTer Simulink model and all the way back with the sensor values. So this is where the fun begins. I can't, talk about crypto without talking about math, so I apologize. But I'm going to be glancing over a bunch of the math, but I'll try to contain my excitement. I love it. It's very elegant and beautiful. But nevertheless, the encrypted controller was realized by building a lattice-based crypto system using the learning with errors problem. Before I can talk about what LWE is, I'm going to present what learning without errors is, just as a pedagogical point of view. So suppose we have some secret vector S that is in a set of integers modulus Q. We sample some public matrix A, square matrix for this case, that is uniformly sampled from the set of integers modulus Q, and we compute this Greek letter nu term. We take the public matrix A multiplied by the secret vector, mod Q it, and the problem asks, given the following system of linear equations, can we learn the secret vector? And if you've taken linear algebra, you'd be able to easily say, yeah, of course, we can use Gaussian elimination, or we can invert the matrix A, and we can easily provide a solution in polynomial time. What's very simple and beautiful about the learning with errors problem is by learning the secret key by just simply injecting noise, perturbing the system with some errors, makes the problem post-quantum secure. And this is actually known as the search problem. And if anything, I want you guys to come away with today is that this is one of the foundational problems of the post-quantum cryptographic schemes that NIST approved a few months ago. These are lattice-based problems, and this is the learning with errors problem. So let's go through what that is. The problem statement is the same. We have some secret vector S. We sample the same public matrix. But what's new here is we have this error vector, which we sample from some chi distribution of our choosing. Typically in literature, it's a discrete Gaussian distribution or uniform distribution. But nevertheless, it's the same Greek letter nu. We take the public matrix A multiplied by the secret vector, and then we inject our error terms into that. The problem states, given the following system of linear equations, can we learn the secret vector from this set of noisy equations? And it turns out it was proved that there's no polynomial time that algorithm that approximates these lattice problems to within polynomial factors. It is average case hard. So it has been proven to be post-quantum secure. And as I mentioned, it is the underlying hard problem, much like prime factorization or the discrete log problem in a lot of post-quantum secure crypto systems. So how do we do that? I apologize again, more math. I'll quickly glance over some of it. and I'll only highlight the things that I want you guys to take away. So our goal here is we want to instantiate some crypto system to build a public key encryption scheme. And what we want to do is we want to encrypt sensor measurements, again, at the sensor interface. We want to decrypt actuator commands at the actuator interface. So we'll start with key generation. For some lambda bit security, we could generate the secret key and the public key. And this should look very similar to the previous slide. Our secret key is just going to be a long column vector of size cap n. The public key, we're going to use our public matrix, which we've uniformly sampled. And then we, again, compute this Greek letter new term. And we know based off of the LW assumption that our secret key is safe within this new term. Encryption, we're going to denote encryption for an LWE ciphertext as this function here has two inputs, the public key and whatever our message is. In this case, is the sensor measurements. And it's going to produce some ciphertext that is going to be a long vector of dimension size of the size of the secret key plus 1. And I provided the math here. It's just linear algebra. When these slides are distributed, please go through them. It's very simple, but it seems intimidating, but it's very simple at the end of the day. But I just really want to address your attention here to the ciphertext pair that we have, because I'm going to be using those throughout the definition. So we have this script C sub 1 and script C sub 2 as our ciphertext pair for the ciphertext itself. All right, so let's move on to decryption. Assume we have a correctly formed LW ciphertext that we want to decrypt at the actuator interface. The decryption algorithm that we use is just the inverse of the LWE ciphertext, or LWE encryption algorithm. The math here, everything cancels out, but I just want to note to put your attention to these last two equations here. Within those rounding brackets, we have the error term plus our message. This becomes a very important property within FHE, is this successful decryption property. As long as that error that we perturbed our system is sufficiently small, that rounding term will squash the error and we'll be able to successfully retrieve our message. Unique to FHE schemes is as we perform these homomorphic operations, we end up accumulating more and more noise or these error terms that we use for security purposes to begin with. So this successful decryption property is going to become in handy on the next few slides. And again, this relationship or this threshold Q over 2T is just a relationship between our ciphertext modulus space and our message space T. But nevertheless, I'll show you how those accumulation of error terms show up in homomorphic addition. It's a straightforward operation. So suppose we just have two signals that we want to add together. They're both correctly formed LWE ciphertext C and C prime. Adding them straightforward, we take those ciphertext pairs and we just collect like terms. And again, if we were to unravel these Greek letter new terms that we built in our public key, we get these accumulation of error terms. So again, hopefully I can show you that we accumulate these errors as more operations happen in the ciphertext space. And as we accumulate these error terms, our probability of a successful decryption goes to 0. So this is something that we have to be aware of whenever we are performing our excuse me, as we're performing homomorphic operations. All right, so homomorphic multiplication is a little bit more involved, and the reason why it seems more involved and more complicated is because, again, we're trying to manage the noise growth in our operations. To do so, we have to introduce this Gentry-Shaw-Hay-Waters ciphertext or GSW ciphertext. And our goal here is to use the GSW encryption to encrypt a control system parameter or control system gain, then perform homomorphic multiplication between a GSW ciphertext and an LWE ciphertext. So here's the definition for our GSW ciphertext or GSW encryption. We use our public key and our message that we're using, which is the control system parameter or gain. And it yields what I'm denoting as a boldface C ciphertext. And if you note, the dimensions of the GSW ciphertext is a lot different than our LWE ciphertext. It actually yields a large matrix when compared to the long row vector of our LWE ciphertext. So where does that come from? It comes from using this thing called the gadget, which is what GSW came up with. The gadget matrix is this blue box. Again, I would love to talk about offline or if these slides are distributed, you can please go through them. But the gadget, what it is it is a Kronecker product between the identity matrix and something called the gadget vector, which just ends up being a vector of a base of our choosing raised to the power of some script L-1. And there are good and bad choices for these parameters, which I cannot go into for the sake of the time, but nevertheless, moving forward, homomorphic multiplication with the ciphertext requires even more functions and even more elegant math. It requires something called the gadget decomposition transformation. And what this function is, this decomposition function, G inverse, takes a vector and makes it into an even longer vector. But we can actually just look at what the definition is here. So if we have some vector, capital lambda, all it does is it takes its elements and it decomposes it with respect to some chosen base. So if we had some vector that was all elements were in base 10, all we're doing is we're decomposing those elements, say, into base 2. So we're gonna lengthen our vector at the sake of having smaller element entries. And again, there's a reason for all this. It's to manage the noise growth, which I'll get to in a second. An important property is this gadget inverse property. Anytime we flatten a vector or use this decomposition function, we can compress it back into its original form by multiplying it by the gadget matrix, which I showed in the previous slide. And again, if these are distributed, here's an example with some easy parameters you can go through to check my math to hopefully make sure everything I have up on the screen is correct. Okay, so how can we use those tools to perform homomorphic multiplication? Let C be an LWE ciphertext, and let the boldface C be this GSW ciphertext, and we just want to multiply them together. So the GSW ciphertext is some gain and some arbitrary signal. We want to multiply them in some homomorphic space. What we do is we apply that flattening or that decomposition function to the LWE ciphertext, and then we can just perform vector matrix multiplication with the GSW ciphertext, and it produces an LWE ciphertext whose message is multiplied by the gain and the arbitrary signal. And again, if these are distributed, please go through this little sanity check to show that, yes, all of the dimensions line up and that the result is actually indeed an LWE ciphertext. But again, this is all by design. Noise grows, but it's carefully managed by the gadget structure of the decomposition. Decomposing our LWE ciphertext yields smaller entries, preventing multiplication from blowing up the noise, potentially causing the successful decryption property to fail. So again, it is all by design. It's all about managing that noise growth and trying to preserve that property of a successful decryption. So how can we use these ingredients to build our encrypted controller? And this is how we did our controller in the loop method, or the hardware in the loop method. Prior to system startup, we generate the public and secret keys according to some lambda bit security. We perform GSW encryption on the proportional gain. And then system startup, the operator sets the reference temperature and is encrypted. So for our simulation, the operator is putting the temperature reference they want the reactor to be at 650 degrees C. At every time step K, the controller samples and encrypts the outlet coolant temperature of reactor 1 and at the sensor interface produces a LWE ciphertext of that temperature. We then go on and compute the proportional controller homomorphically using the proportional gain control law, and also using the definition of homomorphic multiplication. And then we send that encrypted command to the actuator for decryption to go on and to control the raw position, to then go on to control the reactivity, which then goes on and controls the temperature of our reactor. These are our results. The main takeaway here is that it does not degrade the performance when compared to its plaintext counterpart that you can see visually. I have a table here of the parameters that we chose when we instantiated our PKA system, and I also provided the typical parameters that are chosen for the choice in those parameters. And I'll get to why we turn those down in a second. Another issue besides time complexity with FHE is space complexity. You can see that the encrypted controller, especially with the GSW, because the GSW ciphertext, it is, thank you, a large matrix that we hide our message in. And you can already see that the ciphertext blow up and space complexity is there. But I know there's some control theorists in the room, and you might notice, hey, there's a steady state error. Robert, you're taking a victory lap. You said you controlled something homomorphically, yet you're not even getting to your reference set point. That is because we're using a proportional controller and some future work, which I can confidently say that we've already done since the publication of this. We need to get creative with some homomorphic algorithms for memory-based control systems. We have this integral term that impacts the noise accumulation during homomorphic processes, which then again goes back to interrupting that property of a successful decryption. And also, we need more of a formal analysis when varying these LWE parameters on this side. There are critical design choices that impact security, functionality, and efficiency that we need to be more formal about, rather than just picking things to ensure that our controller performance does not degrade over time. And with that, I thank you guys for your attention. By developing a method to design and realize LWE integrated controllers, we can achieve end-to-end encryption to thwart cyber adversaries to meaningful ends. I have a QR code for the FHE.org community. I'm a contributor with them. They have an active Discord. If you guys are curious about FHE or the state of the art of it, they're more than happy to help. And with that, I thank you for your time. Thanks.
We have one short question. So have people